So the topic today is an introduction on how to build a ray tracer. So the task of ray tracing is to build photorealistic rendering. For example, this is a cornell box. The left one is a photograph of a cornell box that from like 1960s, I think, from some lab in the Cornell University. And the right-hand side is generated by computer graphics with path tracing. And you will notice that it is really hard to tell which one is real and which one is not. But before we start, wait. I think I'm using the wrong slide. Am I? Oh, I'm using the right slide, sorry. So before start, I will talk a little bit about the background of the ray tracing. So first at the beginning, there is the render equation, which is very complicated math, but the idea is simple. The output radiance of light is equal to the emission of the lights plus the integral of the contribution of all the incoming lights. So I will not explain the term because some of them are cut off from the slide, but just this is a general idea of what is going on. Sorry about this. And there are two kinds of algorithms for ray tracing, for rendering. One is object order rendering, and other is image order rendering. So rasterization, which is used by most of the GPUs nowadays, even though RTX start to use ray tracing, is an object order rendering algorithm. And it is a lot like how we paint a picture. We just draw one thing at a time. And then if we have something that is in front of another thing, we just overwrite the other things. But for ray tracing, it's totally different. For ray tracing, it's image order rendering, which means for each pixel, we draw them independently. And we don't need to consider the orders of objects. And ray tracing is very slow compared to rasterization. But however, there are a lot of effects that can be really hard to implement with rasterization. For example, those two images, the left one is generated by rasterization and right one is generated by hybrid approach with some ray tracing. And you can see, despite the left-hand image use some advanced screen space tricks to mimic the reflection and other effects, it still cannot be as good as the right-hand side image, especially for the mirror reflection and the shadows for this semi-transparent object. Now let's talk about a bit about ray tracing. Start from basic recasting. So the essential part of recasting is to generate a ray and do a ray intersection, and finally do the shading, which is just calculate the color of that intersection point and then just return that color. The pseudocode is the following. First, we compute the viewing rays of that pixel, and then we find the first object hitting the ray and the surface normal. Finally, we calculate pixel color from the hit point light and the normal. So there are two kinds of projections or two kinds of cameras that we can use to generate rays. One is the orthographic camera, and another one is perspective. So orthographic projection is useful in CAD applications when we want to design some stuff and we just want to have this kind of parallel view, but it is not realistic. So the perspective camera is more like real, closer to the real view of how things look. And then with the concept of camera, with the concept of projection, the next step is to actually represent a ray. So ray itself can be represented as a function, which is it takes a number and then the number t is the displacement from the origin to the ray, and then we can, with that number t, we can get a point which is on that ray as a result. And the ray structure itself can be represented as origin and direction. And as we said before, there are two kinds of projections, orthogonal projection and perspective projection. For both of them, we need to construct what we call the orthonormal basis. So it's 3-vector UVW. We can calculate them by the cross product, and then we can construct rays this way. I don't think I have pseudocode for this part, but it is easy to find such a kind of code online. The next step, let's talk about ray object intersection. So for ray object intersection, we need a function which is that takes a ray and returns a hit record, but it is not guaranteed to have an intersection. So that's why we have a return optional hit record. By the way, all the codes are pseudocode, so there are no languages look like this. It's just some kind of pseudocode in the syntax that like basically. And I will only talk about sphere, since sphere is the simplest kind of shape we can talk about in terms of ray object intersection. A sphere itself can be represented as a center and a radius. So center point and the radius. And for ray sphere intersection, first the ray is a function that takes t and can be represented as origin of the ray plus t times the direction of the ray. And for the sphere, there is the implicit representation of the sphere. With the center and the radius, we can say, give a point P, whether the point is on the sphere or not. And look at the formula here. If P is P minus C square minus R square is equal to 0, which means P minus the magnitude of P minus C is exactly R. So that means our point is on the sphere. If this number is positive, that means our point is outside the sphere. And if this number is negative, that means our point is inside the sphere. But we don't care about those. We only care about whether our point is inside, is on the sphere or not. That's why we say it's this equation equal to 0. And then we just do some high school algebra with those two. We combine them together, do some substitution, and do some simplification. We get an equation with a t squared term and a t term and a constant term. R is a constant because R is just the radius of the sphere. The only variable here is t. And this is a quadratic equation. So if you can remember from the high school algebra, we can solve the quadratic equation by calculating delta. And this solution of quadratic equation have some physical meanings. If there are two positive roots, that means we have two intersection points, and the smaller root is an intersection point we want, and the larger one we just ignore that because we already intersected here, and then the ray will do some kind of scattering at this point. So this point is not valid anymore. If we only have one root, then the intersection point is tangent to the sphere. If I have one positive and one negative root, that means we have a ray shooting inside the sphere. So we just ignore the negative root and only use a positive one. The last case, if we have no real root, that means we don't have intersection at all. And with real object intersection, I only demonstrate how to do it with spheres, but you can see we can also do that with triangles and other kind of shapes, even though they are more complicated than spheres. Then we can try to find the closest intersection for a thing. But first, we need a data structure to store the object in a thing. In here, I will just store the thing as a list of object and list of light. Later, we will talk a little bit about accelerating data structures, where we will change this vector into a tree representation. And the intersection function for thing is simple. We just run a for loop and it intersects for each individual objects and find the closest one. As a result, we can have this kind of image where we have ray object intersection, and if it intersects, we returns the color of the thing, of the object. For rectangle intersection, it is a bit more complicated, but the general idea of rectangle intersection is triangle is always reside in a plane. So we can calculate where the ray intersects with that plane, and then we just use barycentric coordinates we calculate the barycentric coordinates of that point on the plane and say whether that point is inside the triangle or not. The next part is shading. So the idea of shading is to calculate the light and then get the actual color on that particular pixel. The simplest kind of shading is the Lambertian shading, which is the idea that if light scattered kind of semi-randomly on the surface, then the mirror reflection should have the strongest kind of scattering, and with the angle become smaller and smaller, then the light scattering become also smaller. So, but this Lambertian reflection is, the Lambertian shading is also pretty dull. It looks like plastic. So There's this improvement called plane phone shading that add a specular term, use the half angle of the light and the view angle, and with that we can have something looks more like a metal. And for multiple light sources, we can just add the contribution of all the light sources together. And with that, we can modify our rays, say, intersection algorithm a bit to, sorry, not racing intersection, but after we find the intersection point, we just call, if we have any intersection, we call this shading function to calculate the color at that point. Otherwise, if we don't intersect, our ray don't intersect with anything, then we just retain the background color. And for the shading itself, we just use the for loop for multiple lights, and for each light, we use the formula that we had before for plane phone shading. I don't have a picture here, but the next step is shadow ray. So for shadows, the idea is we can shoot a ray to the light source. And the point P, because this ray is occluded by this object, that means it is inside the shadow. And sorry, point Q. And point P, it is not occluded by the source, so by this object, so it is not in shadow. And this text is wrong. So this is the basic idea of doing how to do shadow in ray tracing. It's very simple compared to the rasterization shadow mapping or shadow volume approach. There's one problem left, which is called self-shadowing. The reason of this is because of numerical instability, that if we have ray that we calculate, when we ray surface intersection, when we calculate this intersection point, we may actually get a point at here. And then when we shoot a scattered ray, we may get a intersection point again with the surface itself. As a result, we will get this kind of image. So the way to solve that is to have a displacement when we calculate the shadow ray. So this way we can avoid this artifact. And for the shadow implementation, for the shading part, it should be almost the same if it is not in the shadow. And as a result, we can see this image with nice shading, but also with shadows. Next is recursive ray tracing. So I think in 1984, Turner Whitted introduced the recursive ray tracing, which really kind of make what is impossible to do in rasterization and trivial to implement in ray tracing. So, okay, it's not 1984, but 1981. This paper called an improved illumination model for shaded display, where you can see this kind of nice refraction, and it didn't have much reflection in this scene, but the idea is light can scatter through a path multiple times. And For our simple ray tracing, I will only implement ideal specular reflection with this reflected ray is equal to the inserting ray minus the 2 times the dot product of the inserting ray times the normal vector and then we can just do this method here to calculate the reflecting ray. We still do the previous shading step, but then we recurse our ray tracing algorithm to get with that. This should be depth -1, sorry. And if +1 because I use depth greater than 10 here. So if depth is too large, then we just quit. As a result, we can have multiple bounces, like we have a ray hit here, and then it have a reflection that hit here. So with that, we implement mirror reflection. We can use similar technique to implement refraction. So then we can have the nice image as the Turner-Whitted paper showed before. The final step is accelerated data structure. The idea is that calculating ray object intersection can be expensive if we have a lot of objects. For example, if I have 1 million of triangles, then we need to calculate every ray to intersect with every single triangle. But that's not actually the case. For example, if we have this model and we have a ray like this, we can see that this ray intersects with this red box. So we need to check further whether it intersects with this shape or not. If we have ray that goes from here, then it's not intersect with the red box, then we don't need to check whether it intersects with individual triangles or not. And then we can recurse these steps. So if the ray intersects with red box, whether our ray intersects with this part of the shape. If it is not, we don't need to check every triangles in here. Instead, we just check this part. And we can recurse further and further. This way, we change order of n algorithm into an order of log n algorithm, because we are doing a binary, we work through a binary tree instead of just do a linear search. And for the bonus point, so far I'm talking about algorithm called weighted ray tracing, which use one sample per pixel and shadow rays. Path tracing is another algorithm that if we talk about ray tracing in movies nowadays, they are usually path tracing. And our final image looks like this. Notice that we have hard shadows here. And we can go very far with this approach. However, the shadow is still hard, and not all the effect can be generated by our ray tracing approach so far. And for the path tracing, we just shoot multiple rays per pixel. Instead of using shadow rays, we just directly bouncing those rays until they hit a light source. And with that, and then we don't do any kind of direct shading calculation at all. Instead, our material use something called a probability distribution, so called bidirectional reflective distribution function to calculate the scattering of light. As a result, we can have this really nice kind of image that looks almost real. And as I said before, we use random sampling to calculate the scattering. The downside of path tracing is it is way more expensive than ray tracing. It's like 100,000 times more expensive than weighted style ray tracing. So look at here, with 100, 200 sample per pixels, we still have really fuzzy image. Only with like 10,000 samples per pixel, we converge to a nice looking image. So on the other hand, the algorithm of path tracing is actually simpler because we don't need to do shading. We don't need to worry about shadow ray anymore because path tracing will just automatically handle those for us. And we have nice soft shadows look like this. Also for ambient occlusion, which is the idea of that we will have darker corners, this kind of effect will just work for path tracing without any kind of additional trick. So the challenge of ray tracing, of course, is it is slow. It is way slower than rasterization. Even with RTX, people still need to come up with a lot of clever optimization to make ray tracing fast enough for video games. So we need to some ways to reduce the works of ray tracing. One way to do that is denoising. Denoising combines multiple approaches, including spatial reconstruction, temporal accumulation. Like if you follow Twitter online with graphics programmers, people like to talk about something called TAA, temporal anti-aliasing, and also neural networks. The neural network is usually not used in games because it is still not fast enough for 60 FPS. With denoising, we can do path tracing with way less sample per pixel, and then we can generate image like this, and with a really fast algorithm to make this image look like this. And one hard problem for real-time ray tracing is accelerating data structure construction and updating, because for real-time ray tracing, objects in video games, object actually moves, and accelerating data structure as tree structures cannot move that easily. So there is a trade-off between quality and the speeds. The highest quality accelerating data structure may not move the fastest because we want to move the object and reconstruct them in reasonable speed. But also reasonable accelerating data structure that construct very fast may have lower quality, which means we need to longer time to actually render that thing. So there's a trade-off between how to do accelerating data structure to have the best performance. Of course, we can just buy better hardware. RTX 2000 is not good enough, then 3000 Titan or whatever, and then, but that is not an option if we want to build a game that everyone can just run on their computer, for example. there is another thing to consider, which called load balancing. The idea is like that. With normal tile-based workload distribution for the GPU, like for each thread will launch one of the tile, we will have this problem of, for some tiles, for example, this one with this spotlight, it will be a lot more costly because you can think about light bouncing around inside the spotlight compared to the ground like here. So one way to solve that is to use a scanline-based workload distribution, where instead of tile-based, we just distribute one line for each thread. And this way, we will decrease the possibility of having one thread that work way longer than other thread, and then every thread need to wait on that thread.